So we're getting into polynomials, which if you remember from Algebra 2, we started out by naming polynomials. They were given a name by their degree. Do y'all remember what the degree means? Degree is the largest exponent. So if the largest exponent was a 4, we learned that that was called a quartic. And then if it had two terms was binomial. In our notes, we listed out the degree, the number of terms, and we gave it names. We're going to be doing a lot with polynomials, but it's not going to be, we spend a whole day talking about naming them. We'll move a little faster than that. So a polynomial, here's like the formal definition, and it looks really like complicated and real ugly, but a polynomial function is any function representation equivalent to the analytical form, blah, 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 all of this. Basically, you got a number with an x to some exponent, plus another number with an x. So like if your first one had an exponent of 5, then you would have another number, x to the 4th, then x to the 3rd, and then just x, and then just a number. That's a polynomial. You've seen them. It's nothing new. So in general, the leading term is the whole term in the front, like the number, the variable, and the exponent. Now, I want to say it's always in the front, but remember your polynomial is supposed to be written with the exponents going biggest to smallest. If it's not in that correct order, it won't necessarily be in the front. It's basically the term, the piece that has the largest exponent. So in this case, this whole thing right here in general is the leading term. So it's some number x to some exponent. Okay. We're going to look at this in general. Once we get to like examples where it's just numbers, it'll be a lot easier. The degree is the largest exponent. Okay. And so in this case, it's just going to be n. The leading coefficient, so the coefficient is the number in front of the x. So the leading coefficient is the coefficient of the first term. In this case, it's just an. Some things you need to know for it to be considered a polynomial. There's no x in the exponent, and all exponents are positive. So these first two examples, we're just going to list the leading coefficient and the degree. So number 1, the leading coefficient, and if I look, it is in the correct order. Okay, so the 3 that's in the front, that's my leading coefficient, and my degree is the largest exponent, which is 4. The leading coefficient is the number in the very front. The degree is the largest exponent. Now, if you'll notice on number 2, this one is not in the correct order. Really, this negative 7x cubed should be in the front because it has the biggest exponent. So what do you think your leading coefficient is? If it was in the right order, what would be the number in the very front? The negative 7. Negative 7. So even though technically in this, it's 12 is in the front the way it's written, but it's not written correctly. If it was written correctly, negative 7 would be your leading coefficient. And what's the degree? 3. So this is a cubic. This one is a quartic. What about the degree of 5? Quintic. A degree of 2 is a quadratic. So something else that you can do is if I give you a table, you can actually find the degree. And what you do is like you take the first difference, the second difference, you keep going until all of your numbers are the same. So you do the first difference, second difference. If they're all the same the third time around, it's a third degree. If it's the fourth time around, it's a fourth degree. Okay, so I'll show you. So if we find the first difference, now I don't think any of you grabbed your calculators. These get to some big numbers. If you want to come grab your calculator, let me see. You're actually not going to need it for the rest, so I'll just do it on my calculator. Well, how do you get from 45 to 5? Subtract 40. You can get that one. From 5 to negative 3, minus 8. So negative 3 to positive 69 is 72. And then if you take 653 minus 69, get 584. And then 2565 minus 653 is 1912. So it's not a first degree because those numbers are not the same. If it's a second, remember we learned linear and quadratic. First degree if they were the same, it's linear. Second difference if they were the same, it's quadratic. Third difference if they're the same, it's cubic. So we'll keep going. From negative 40 to negative 8, you add 32. From negative 8 to 72, you add 80. From 72 to 584, you add 512. Still not the same, it's not a quadratic. So let's see if it's a cubic. 32 to 80 would be 48. Or 32. It's not a cubic. So if these were all the same, it'd be linear. If those were all the same, it'd be quadratic. This one will be cubic. $384. And we get 384. So the degree is 4. Now, if those weren't the same, I wouldn't have enough numbers in my table to figure it out because I wouldn't have any more to check. Now, something else that we also learned about in Algebra 2 are maximums and minimums. And I briefly brushed over the vocabulary relative max, but I said, we don't have to worry about that in here. Now we do, because we have something called a relative max and an absolute max. So we're going to have to decipher between the two. So in general, maximums and minimums are just called extrema. That's just the way to group them all together. So the extrema of a graph are the max and min, or maximum and minimum points of a function. And there are two types of extrema, two types of max and mins. The one that you are familiar with from Algebra 2 is called a relative max or min. Relative or local, those words are different. A relative min is the most common, but also local min. So a polynomial has a relative max or min where it switches from increasing and decreasing. So it goes back and forth. So it's the top of the hills or down in the valleys. So the hills and the valleys. Those are your relative max and mins. Also, if there's an end point, and I'll show you an example. This is one of those things that, you know, that I told you that there's some like heated debates about, like in the Facebook groups and within the pre-cal people, whether or not the endpoints should be included. Some people are like, oh, of course they are. Or some people are like, no, they're not. Well, College Board, the people that are making the test, say if it's an endpoint, we include it. I'll show you an example. Alright, so if it's an endpoint, it's included. Now, absolute max or min, which is also called global, of all of your maximums and all of your minimums, it's the highest or the lowest. It's the highest of the hilltops and the lowest of the valleys. So relative, you include all of the hilltops. Some are higher up than others. Absolute is the very, very top. So, of all local maxima, or all the local maximums, plural maxima, the largest is called the absolute maximum. And the smallest of all the local minimums or relative minimums is called the absolute minimum. It kind of makes sense. The absolute max is the highest one. All right. So, here's an example. We have two hilltops. So those are the max. So the hilltops are our maximums. And then we have one valley minimum. But this, when I said endpoint, this is what I'm talking about. It's an endpoint. It counts as one of our, and it would be a minimum because the graph it's down here. So that would be considered a minimum. This arrow really means that this graph continues forever. Okay. So the local or the relative minimums, we've got two. It's just asking for the x values there. So I have a minimum at x equals what? What's the x value here? -4. And another minimum at 0. Yep. And then a local maximum, a relative maximum at x equals -2 and 3. Now the absolute maximum, so of these two, which one is actually the highest? The left one or the right one? The right one. And I don't know if it's always the case, but all of the notes that I've seen, when it asks for the absolute maximum, it also asks for the y value. So the absolute maximum, the highest that it goes, is at 2. The y value there is 2. The x value there, it also asks x equals 3. So the absolute maximum, the highest that it goes, is a 2. The x value there is at 3. Now the minimums, we have this relative minimum, but over here, this one goes on forever. If it goes forever, you cannot find the absolute minimum. You could not find the lowest that it goes. It would be going on forever. Well, you don't put infinity or negative infinity there. Just put none. So if you have like an arrow going down, you can't have a maximum or minimum that way. Okay, so notice this is not your absolute minimum. It's one of the relative minimums, but since your graph goes forever, you cannot find a lowest point. There is no lowest point. Alright, so here we have another one. So this would be a max. These are arrows, which means it continues forever. Okay, so there aren't even relative minimums on this one. You cannot have a relative minimum, like an arrow is not considered a minimum. So there are no valleys on this example. Okay, so there's none, no relative, and no absolute minimums. Okay. I have one relative max, which also happens to be my absolute. If you only have one and there's no arrows going up there, if it's the only one, then it's the absolute. It's the highest of them all. So my local maximum is at x equals 1. That also happens to be my absolute maximum. The maximum itself is 3 at x equals 1. See if you can do this next section. Notice this one is an endpoint. This is an arrow. So try that. Alright, so hilltop, max, valley, min, this would also be a max. So you should have local minimum at x equals -2, local maximums at x equals -4 and 3. Now, of those, the absolute maximum is at 2 when the x is 3. The absolute maximum is 2. The highest that it goes is 2 at x equals 3. And there are no absolute minimums because it goes down forever. There's no way to find the lowest part on the graph. Any questions? Try this next one. Alright, you should have local minimums there and there at x equals -3 and x equals +3, and then local maximums at -4, 0, and 4. So those are all the x values. Now of these, the absolute maximum, the highest is this one. So the absolute maximum is 4 at x equals 5. Oh, that should have been 5, shouldn't it have? I put 4 there, that should have been 5. And the absolute minimum, in this case, we do have an absolute minimum. It's -3, which happens at x equals -3. Any questions? So here's just two important facts to know. If you have two x-intercepts, you got two x-intercepts, which are also called zeros. Taught you about that in Algebra 2. You will always have at least one local max or local min. So if you have a 0 at 1 and 5 or a minimum somewhere between 0 and 5. At least one. There could be more, but you have to have at least one. That's just the way polynomials work. Something else. Polynomials that have an even degree. So a degree of 2, a 4, a 6. They will always have either a global, and I'm trying to interchange the words so you get used to them. Global means absolute. So they'll have either a global max or a global min. Okay. So if you have an even degree, you will have a global max or a global min. You will not have both. And then the last thing we're going to talk about before you do some practice, points of inflection, which we've already briefly went over a little bit. Again, this occurs when a function goes from concave up to concave down. Those do not happen at the max or mins. Okay, so if you have, if I drew that point of inflection was probably about right there. If you were finding the rates of change, it's where those rates of change go from increasing to decreasing, or vice versa. That's where those happen. So if we're looking at this example, we want to look for the points of inflection. So, and if you look really close, if I, you know how I draw the little slopes? If I'm drawing those just by nature, I'm going to draw them there, and then my brain switches to start putting them on top, just because of the way the curve goes. That's a good indication that that's my point of inflection. So here, my brain wants me to switch from drawing them on the top to on the bottom. Because if I try to draw them here, I'm going to be hitting my graph. So that's kind of just if you are drawing them now, you may not be paying that close of attention. And like I said, usually they happen, like this minimum here is at -2, this maximum is at 0. They generally happen about halfway between at x equals 1. There's no real way to say that in pre-cal. If you take calculus, that's when you learn that. So points of inflection, we can estimate that they are at x equals -1 and x equals 1. So for each of the intervals, we're going to determine if the rate of change, those are the little slopes, are getting bigger or are they getting smaller. Okay. And remember, if the rate of change is increasing, what do you know about the graph? Concave up. If the rate of change is decreasing, it is concave down. So from 3 to 4. Would I say the rate of change is increasing or decreasing right there? I would say that it's increasing because the graph is concave up. From -1 to 1. That's that section. Are the slopes increasing or decreasing? Decreasing. Because the graph is concave down. And then what about from 1 to 2? It switches from concave down to concave up right there. That's your point of inflection. So it would be increasing because it's concave up. All right, last thing. But here's, I've given you an interval from 0 to 3. The number of cars in the parking lot is modeled by this function. How they got that function, I don't know. Based on this model, at what time is the number of cars, what time does the number of cars change from increasing to decreasing? And you don't have your calculator, so I don't even know if this is going to fit. 1.37 x to the 5th plus 4.218 x to the 4th minus 0.357 x squared plus 3. So the number of cars change from increasing, oh gosh, to decreasing. So we're not talking about the rate changing. If the rate was changing, we'd be looking for a point of inflection. We're talking about the graph. The function is the number of cars. So we're looking at where the number of cars changes from increasing to decreasing. Ugh. So, I don't like this one. Where's zoom fit? There it is. So that means I am going, that's not what I want either. No. I had a meeting with pre-cal teachers, and somebody, that NumWorks calculator that I just briefly told you about, it's really cool. Like, the graphing capabilities on it are awesome, and like just to big stuff that we're going to learn that you have to memorize something later, that is on the calculator, which is awesome. Now, you can't use the calculator on all parts of the test, but it's still nice. Alright, so trace right there is the maximum. So that's where it changes from increasing to decreasing. Increasing to decreasing is a max at x equals 2.424. That's the number of hours.